Hey guys, welcome to CodeChef's YouTube channel. The problem that we are going to discuss today is product pain. The problem appeared in November 21 Cook-Off and SnackDown 21 pre-elimination and has a difficulty level of easy. The prerequisites to solve this problem include math and binary search. The problem statement goes as follows. For a given array B1, B2 up to Bm, that is an array of length at least 3, let's define the weight as the largest value of Bi minus Bj multiplied by Bj minus Bk. So this expression is given to us and the weight of the array, any array of length at least 3 is defined as the maximum value of this expression over all the possible triplets I, j, k such that all the indices I, j and k are distinct. Okay, so this is some information given to us, some definition. Now the question is or the problem is that we are given a sorted array A containing total n elements and it is sorted in non-decreasing order, that is A1 is less than equal to A2 and so on up to the last element. So what is our task? Our task in this question is to calculate the sum of weights of all the possible subarrays of A of length at least 3. So we'll be given an array A. Now for all the possible subarrays of this array, we have to calculate the sum of their weights. And what is the weight of an array? It is defined above in the problem statement as we just saw. So let's understand this with the help of an example. Say the array given to us is simple, that is 1, 2, 3 and 4. So total 4 elements are present and they are 1, 2, 3, 4. Okay. So first of all, how many subarrays of length at least 3 are present in this array? So the answer is 3. That is, one array is 1, 2, 3. Another one is 2, 3, 4. And another subarray is the array itself. That is 1, 2, 3, 4. So in this first array, because there are only 3 elements, I, j, k have to be amongst these 3 only. So if you fix I over here, j over here and k over here, you will see that the weight of the array comes out to be 1 and 1 is the maximum weight possible. Okay, that is 1 is the maximum value of bi minus bj into bj minus bk. Similarly, here also if you fix I over here, j over here and k over here, you will see that you get the weight of 1. And you can check for yourself, try all the possible triplets, 1 is going to be the maximum weight. Okay. Now, in the third array, in the third subarray, that is the whole array, if you fix I over here, say j over here and k over here, you will get the value of expression as 2. Okay, that is basically 1 minus 3 into 3 minus 4. So what? This comes out to be 2. And 2 is the weight of this array. Again, why? You can try all possible triplets. This is going to be the maximum one. So what is going to be the answer for this array? This input array, the answer is going to be 2 plus 1 plus 1. That is total 4. We have to sum all the weights. Sum of weights of all the subarrays of length at least 3. So with this example, I hope the problem statement is clear. Now let's understand how to approach the solution. So the solution approach goes as follows. First of all, let's fix an array small a which contains the elements a1, a2, a3 up to an. Okay, so we will first solve the problem for this given array. Okay, that is considering this array as our subarray. Okay, the input array given to us, capital A, will contain many such subarrays. So let's solve the problem for one such particular subarray. Let's call it small a. Okay, so we have a total of n elements in this array. We are fixing total of n elements in this array. Okay, so the expression that we have, expression looks like this. that is AI minus AJ multiplied by AJ minus AK. So because we have been told that the weight of the array is the maximum value of this expression, we'll always try to get such a value that is first of all greater than equal to 0. And it is easily possible as well in our case. Why? Because the array elements are given in increasing order, right? The array input array was given in sorted order. So what we can do is we can pick up any three elements and we can order them in such a way that we will get the value of the expression greater than equal to 0, right? For simplicity, you can assume that choose the first three elements as I, j and k. Even by using that, the expression will have the value greater than equal to 0. So this is established that the expression is always, the weight is always going to be greater than equal to 0. Okay. Now, once we know this, we also know that the values AI, AJ and AK are going to follow some pattern. That is, if this expression has to be greater than equal to 0, then it means that AI has to be greater than equal to AJ and AJ has to be greater than equal to AK. Either this condition is true or the other one, that is the inequality signs get changed. Okay, so if either of these two are possible, then we can say that AI minus AJ into AJ minus AK is greater than equal to 0. So in our case, the array is going to be in ascending order. So let's assume and solve the question for this case. Okay, that is AI less than equal to AJ less than equal to AK. So because this is the case, it also means that, and our array is also sorted. So it also means that I is going to be less than j and j is going to be less than k, because the indices have to be different, right? That's what the question says, that the indices have to be different or unique. So this is also established. Now let's have a detailed look at the expression, that is the expression that we have. So we can infer some more things from it. One of it is that this expression AI minus AJ into AJ minus AK is less than equal to A1 minus AJ, right? Why? Because the array was sorted, right? Our array, if I write it over here, our array A1, A2, A3, A4, this is a sub array of our original array, right? And our original array is sorted. So A1 minus AJ is going to have a bigger value, bigger negative value. So this expression is going to be true, right? Because A1 is the extreme value in our array. Also, if you see, the other one is also going to be true. That is, the same expression is also going to be less than AN minus, sorry, AI minus AJ and AJ minus AN, because the extreme elements, right, in the sorted array. So the value of this expression is less than equal to, first of all, this value, and it is also less than equal to this value. So using both these conditions, what we can say is that our expression, that is basically the weight of the given array, that is A1, A2 up to AN, the weight is guaranteed to exist for I equal to 1 and k equal to n. Okay, so the optimal solution lies for j in between 1 and n. So we for sure now know that if we fix the I as the first element and k as the last element, the answer is going to be for this assignment only. That is, J is going to vary. We don't know for what exact position of J we are getting the maximum value of the weight, but for sure we can say that because the value of the expression lies in between these two ranges, so we can say that I, if we fix I as the first element and k as the last element, then we are getting our optimal answer. So what one can try to do, iterate over all the possible j values. Okay, that is, fix I as 1, fix k as n, and iterate over all the possible values of j, and then find that which is giving the maximum value for this expression. But then again, this would take on time for one subarray. And how many subarrays do we have? We have order of n square subarrays. So that means that the overall runtime of our code would be order of n cube. And that is going to cause time limit for the given constraints of the question. So order of n approach for finding the optimal j is not going to work. So what do we do? Again, we have to dive deep into this expression. The answer lies in this expression only. So if you see that now we have fixed two of the indices, that is I and k. So we can say that the expression is now like this. Earlier it was ai minus aj into aj minus ak. Now it has become, now the expression has become a1 minus aj into aj minus an, right? So these two are fixed values. These two are constants, right? Because they are some particular values which we know from the array. The only thing that is varying is j over a. Okay, so this value, or if you call this as some function of j, this is actually a convex function. That is, its value increases and then decreases. So we can actually find out that for what value of aj this function achieves its peak value. Okay, so actually the peak value of this function, if you find out, it comes at the value a1 plus an divided by 2. So does that mean that we simply take the first element of the array, last element of the array, add them, divide by 2, and then just plug in that value to get the maximum weight? No. Why? Because this is an ideal scenario. Okay, but we have the discrete values in the array, right? So what we have to actually do is we have to find such a value of aj such that it is as close as possible to this value, that is the a1 plus an divided by 2. So that now can be done using binary search. And why we can apply binary search? Because our array was sorted. So what we can do is we can find some neighboring values in this range. That is, we know that the most ideal answer would have been at aj equals to this. But what we'll instead do is we'll find some neighboring values in our array. So let's say our array was something like 3, 5, 6, 7, so on. Some elements before, some elements after. And for some value of a1 and an, this comes out to be, let's say, something around 5.5. Okay, so we will find the neighboring values 5 and 6, and we will find the value of expression at both these values. That is for aj equal to 5 and for aj equal to 6. Whichever turns out to be giving the more value is going to be our weight. Okay, so we only need to check at two possible values of aj. So, and how do we find these values? Using binary search, because we know the value of 5.5. So we can apply upper bound on this and get the value 6, and just the previous value we can get, and we can check that which of them is giving the maximum value for this expression, that is a1 minus aj into aj minus an. Okay, and then that will be the answer for our array. So now we know the process for finding the answer for a fixed subarray, that is A1 to AN. So like this many subarrays we have, right? We have order of n square subarrays. So for each subarray we will be applying binary search. So if we try to predict the time complexity of our code, it is going to be order of n square into log n, because the log n is for binary search, and that is kind of fitting in our given time limit. So this is basically the solution. That is, we fix the I at 1 for the particular subarray, we fix the k at the last element, and then instead of iterating over all possible j's, we know that the optimal answer lies around this value. So we instead apply binary search, and in the vicinity we find the maximum value, and that turns out to be our weight. Okay, so I think the solution is now clear. Now let's see the implementation. So the implementation in C++ goes as follows. We take the input for number of test cases. Now we take the input for array. The array is already sorted, so we don't need to sort it explicitly. Then I create an answer variable which is initially 0. Then I iterate over all possible subarrays, that is the endpoints of the subarrays. So the endpoints are I and k. So I iterate over them, and then I have a function f which takes a index j and returns me the value of the expression, that is ai minus aj into aj minus ak. Okay, and how do I find the value of j? So I apply an upper bound on ai plus ak divided by 2, that is basically a1 plus an divided by 2, just as we saw over here. So a1 and an are the extremes. So for our subarray, ai and ak are the extremes. So I apply an upper bound on that. Then I do a check like j is equals to min of j comma k minus 1. Why? Because by mistake, or not by mistake actually, there can be some input like for which uh, j can be out of bounds, that is out of the range I comma k, so we don't want that. So for safety, I just do the check, that is j is equals to min of j comma k minus 1, and then I just need to plug in the value j to our function and get the value of the expression at 2 points, that is at index j and at index j minus 1, just as we saw over here. We take the value at 6 also, and we take the value at 5 also, because they are in vicinity of each other. Okay, none of them is actually equal to 5.5, but we don't know which of them will give the maximum answer, so we check the answer for both of them. Same is done in the code also. So I plug in the index j and j minus 1, and whichever gives me the maximum value, I just increment that and add it to my answer. So it is done for all possible subarrays, and at the end I have my answer. So this completes the implementation in C++. Now let's submit the code on CodeChef ID, and let's hope for a quick AC. But before that, there are some points where many of you might make a mistake. That point may be, you have to take care that the subarray has to be of at least length 3. So that is taken care over here in my code, that the I begins from 0 goes up to n, but the value of k, it starts from I plus 2. So this guarantees that my subarray is at least of length 3, as stated in the question. Also, while applying the upper bound, you have to be always sure that, or applying upper bound, lower bound, or binary search, the input array should always be sorted. Here, the input array was already sorted, so we don't need to do that check. But always remember that before applying lower bound, upper bound, or binary search, make sure that the array on which you are applying it is a sorted one. Okay, these are some common points where people make mistakes, so you can try to avoid them to save time in a contest. So yeah, now let's submit our code on CodeChef, and let's hope for a quick AC. Great. So our solution works. I hope you guys understood the problem as well as the explanation. If you have any doubts, you can post them in the comments below. I'll try to answer as much as I can.